Hi everyone. In the previous video, you were introduced to some ideas behind control algorithms. Now it's time to learn more about what we mean by control algorithms and learn some examples. So in this video, we're going to be playing around with an RVR. And this is a robot that you may have seen in the Idea Center. It's online, you can buy one, and you can control it through an app on your phone, your iPad, or your computer. And the control problem we want to try to solve is we would like it to drive from where it starts at this line on the right-hand side to this tape on the floor, which is 100 centimeters away. That desired distance that we want the robot to drive, we call the set point. So the set point for all of the code that we're going to be using today is 100 centimeters. The output that we're going to be controlling, we call this the process control variable, is the speed of the motors on the RVR. And so ideally, we're going to be using some logic that tells us how to adjust the motor speed as the distance from where the RVR is to along this horizontal axis to control whether the robot is moving to the left or moving to the right. The first way we want to look at this is similar to what many of you came up with as the best way to control the temperature of the ball in the simulation last class. And that is the idea that we're going to drive the robot, and while the position of the robot, which we get from this command right here, the getLocation.y, while that position of the robot is less than the 100 centimeters, less than the set point, we're going to drive the motors forward, and while the position is greater than the set point, we're going to drive it backwards. And of course, forwards is to the left, backwards is to the right. Otherwise, if this is not the case, we're going to set the speed of the motors to be 0. So we'll run that code, and we can see what happens when we do this. In this situation, the robot approaches the 100 centimeter mark, but goes back and forth. And that's simply because it hits 100, but before the robot can slow down, it then reverses the motor speed, so it just goes back and forth, back and forth. This on-off control that you see here is the first algorithm that we've learned. And it's pretty simple. It just says that if the position is less than the set point, you run the motor forward. If it's greater than the set point, you run the motors backwards. But you can see in this particular control situation, it doesn't work that well. It was great for the temperature control, but it doesn't work in this system. And so this just goes to show that a control algorithm that works well for one problem may not work well for a different one. So you have to experiment to find the best way. So one way to address the shortcomings of the on-off control is by introducing something called tolerance, which basically says how much you are willing to, how much error, how close is close enough to the set point. And we call the distance from that set point that is close enough the tolerance. And the idea you can see in the code is that if the location of the robot is less than set point minus this tolerance, you're going to run the motor forward. If the location is greater than the set point plus the tolerance, you're going to run it backwards. But otherwise, you're just going to set the motor speed to be 0. And what that means is that the robot is going to run until it's within this range of the set point minus the tolerance or the set point plus the tolerance. And as long as the robot is within that range, the robot is just going to stop. And this might be good enough for a particular application that you're using. So when we look at the video of this actually running, you can see that it works pretty well. It goes back and forth a little bit, but once it's inside that distance, it stops. So that's pretty good. Now you can change that tolerance to be different levels. You can make the tolerance really wide. You can make the tolerance very small. And depending on how big or small you make it, the behavior of the robot will be much different. But you can see in the image here that the robot isn't, maybe you don't want tolerance. It's not that close necessarily. It's a couple centimeters off from the tape at 100 centimeters. So what can we do? What's another way that we can do this? If you look at all of these examples, we're using a constant speed for the robot as it's moving along the floor. But if you think about it, another way we might handle this is make it so that the robot, as it gets closer to the distance that you want it to be at, as it approaches the set point, you lower the speed. So here's how we do this. What we do is we calculate an error. We calculate how far off from the set point we actually are. So you see we're calculating an error, subtracting the set point minus the location. And based on that error, we're storing the product of the error times a constant k in a variable called output. And then we are setting that output, we're sending that to the motor. So let's think about this. If the set point is 100 and the location is 50, then that means that the error is 100 minus 50, which is 50. And the output is going to be 4 times 50, which is 200. And so at that distance from the set point, your motors are going to drive at a power of 200. If, on the other hand, the set point is 100 and the location is 80, 100 minus 80 is 20. 20 times 4, that value k, is 80, which means now the output is only 80. So the robot is going to be driving a lot slower at that location of 80 centimeters from the mark, from the set point. And you can see there's some extra code here that simply limits the output values to be no more than 255, because that's the maximum value that you can send to the motors. So it's a little error correction code. And so let's take a look at what this looks like. And so what you see in the video is that as the robot gets closer and closer to that set point of 100 centimeters, the output of the motor decreases, so the speed decreases and it slows down as it approaches that mark. And you can see that in the end, the robot isn't actually right at 100 centimeters. So the performance, the accuracy is similar to what we had with the tolerance. And that might be okay. But it might also be that the output isn't quite enough to overcome the friction that is built in within that robot. So this is a situation where we can actually change that proportion value to be something else. So this says that k is equal to 4. I think it's actually smaller than that in this video. I didn't correct that. I think it's around 1. And so let's see what happens when we increase that k value to be something a little bit more. And so this is an example where that k value is larger. Okay, I'm going to pause that because there's a lot to talk about. So we can see that it goes past the 100, but it actually corrects. It goes past, but then because it's past, the error is actually negative because we're doing the set point minus the location is a negative number, so the output is negative, which means the robot's going to move backwards. So it corrects, knowing that it has gone too far. And the other thing that's kind of cool, and you can see me moving this around, is that while the robot is sitting there, if I pull it forward, it still will automatically correct to go back to that position. It's not perfect, but that ability to self-correct is a really great part of proportional control. So this was, I believe, a value of k equals 4. That last one was about k equals 1. Let's see what happens when we make that k value k equals 6. You can see that the robot goes back and forth, back and forth, back and forth, and even with that oscillation, it doesn't end up right at the 100 centimeters. So you can see that finding a k value that works for your particular application is really important. You want that k value to be perfect in order to get it to very accurately approach that value. But this could be good. You might want it to have that bouncing. You might be able to put up with some of that bouncing. That could be okay. There was one more thing I want to show you, and that is one final algorithm for today, and this is called proportional integral control. You can see that the robot isn't quite at the 100 centimeters. And if we go back to the first example of proportional control, where the robot actually stops short of the mark, what you might do is you might say that when the robot stops short, you know that you are a little bit distant from where you want to be. And so what you can do is add up that error for the amount of time that you are off from where you want to be. You just give a little extra kick that's proportional to the total error that is collected over time. And so I'll show you what that code looks like. This is called proportional integral control. You might see up here that I've added another variable called accumulated error. And all I'm doing is I am adding up the error over time, and I'm adding another number, that accumulated error multiplied by a constant, which is 0.5, to the output. And so this just means that if I'm a little bit off, as I was in that previous video, then just give the robot a little more power, a little bit of a push, so that it can get to where it needs to go. And so this is what that looks like. You can see the robot gets close, and you wait a little bit, and over time it gives a little nudge. It pushes it past, but then it's off, so it brings it back. It doesn't work great in this situation, but you can tune the values so that you get exactly what you want. And this is the fun of control algorithms. It's experimenting to find the best algorithm that works for your particular application. So I hope this helps you understand some different ways that you can go about this control problem. And there are many other algorithms, some of which we're going to be exploring together. But this is just a start. And so you can use this to improve some of the control systems, the control problems that you are using in class. So good luck with the next task.